Welcome to Brain Vision.
So we have a child's motion modeled by the following equation, and I'm just going to leave out the units just for purposes of making it a little easier to read. So we have 46 kilograms, 2.4 meters per second squared, and then 46 kilograms again, times 9.8 meters per second squared. This is in meters per second squared, and this is in meters per second squared, so it's a little different. Times 2.8 meters plus x. So we know x is in the units of meters. This is going to equal a half times 1.94 times 10 to the fourth x squared. So first of all, we'll just analyze this completely numerically. We won't worry about any of the physics. To multiply this all out, we get 132.48, and then plus, well, these two together are 450.8, and then we'll distribute it out, so times 2.8 we get 1,262.24 plus 450.8x. That's going to equal 9,700 x squared. So now we have a simple quadratic. We have an x squared term, an x term, and an x to the 0. So we'll bring everything over to one side, set it equal to 0. We get 9,700 x squared minus 450.8x. And then minus 1394.72, all equals 0. And then solve for x. We get two solutions. One is 0.403 meters, and the other is minus 0.357. So that's just the values of x we get from this equation. Now, working backwards, we want to figure out what this problem, or what the problem could have led to this equation. So if we look now back at the units, well, we have 1/2 times a mass times a velocity squared. So that's like 1/2 mv squared. And then plus, this is another mass, 9.8 is g, and 2.80 plus x is like the height, or at least height plus x, right? And then on the right side we have 1/2, and then newtons per meter is going to be, looks like a spring constant. So we'll say k x squared, and now we have something that looks like an energy equation. So we can say, well, we know the mass of the child is 46 kilograms. The child must be initially at a height of 2.8 meters above the mattress, and the child jumps at a speed initially of 2.4 meters per second. And then we also know, because of the right side of the equation, that the spring constant of the mattress must be 1.94 times 10 to the fourth newtons per meter. So it's basically a child jumping off something onto a pile of mattresses, which is basically what the problem is stating from the beginning. Now we just filled it in with numbers. And if we do what the problem says, which is add the two values of x up, minus 0.357, and divide by 2, we get 0.023, which is basically just the average of the two x values, and that ends up being the distance that the springs of the mattress would stretch if the child were just standing on the mattress without jumping onto it. And you can do the whole calculation out to verify, but that's what the average of the two x values you get. So one is basically as far as down as the mattress goes, and one is as far up as the mattress goes, and you average the two out, and it always happens to work out that the average of those two numbers is exactly what it would stretch if the child just stood on there instead of jumping.